Chapter 11, Part 2, One-Sided Limits. Recall from the last lesson that we established our informal definition of a limit to be the intended height of a function. The actual height of a function is just known as the function value, whereas the intended height of the function is referred to as the limit. So if we consider the graph of the given function, I have a nice smooth continuous curve. I would refer to this as a well-behaved function because it's nice and smooth and continuous. So if I want to evaluate the limit as x approaches 3 for that given function, then I can just look at the graph and I see as x equals 3, the function height is 2, and I can see that as I travel along the curve, I'm not jumping around doing anything crazy. So when I got to x equals 3, that means the intended height was in fact 2. So in this case, just by observation, I can see at x equals 3 the limit is 2 because the actual function value is 2. But then I'd go and do something crazy like this. What happens when the actual function doesn't exist at x equals 2? If I asked you what is f of 3, there is no answer to that question. F of 3 is undefined because there's a hole in the graph. Well, then I simply think about a situation if me and a friend decide we're going to meet up at McDonald's down the street, then the intended destination is the McDonald's down the street. Whether we actually get to that McDonald's is irrelevant to the question of what was the intent. If that McDonald's burned down the night before and we both arrive at that burned down McDonald's, we can never actually arrive at McDonald's because it no longer exists, but the intent was to arrive at McDonald's. So in that case, the limit would still exist because we intended to arrive at the same McDonald's. So to relate that to the given situation in the previous example, let's say I'm arriving from the left and my friend is arriving from the right, and at x equals 3, we have our McDonald's at a height of 2. So I intended to go to that McDonald's, my friend intended to go to the McDonald's, and we arrived at McDonald's. Now, on the other hand, in this case, we have our McDonald's burned down situation, but the two of us still intended to arrive at that same McDonald's, therefore the limit still exists, and the limit is the exact same value as it was before. The limit exists whether the actual location exists or not. The limit and the function value are not directly related to each other. One is not dependent on the other. They can both exist at the same place, or maybe one exists and one doesn't. It's not required that they be linked to each other. And for that matter, what if I have a situation like this? I intend to go to that McDonald's that burned down without knowing that it burned down, but my friend knows that the McDonald's burned down and that they built a new one right next door, and I wasn't aware of it. So I go to the old McDonald's and my friend goes to the new McDonald's. Well, here we have an issue. I intended to go to one location, but my friend fully intended to go to a different location. In this case, does the limit exist? Well, we both have two completely different intents. There's no one clear intended height of the function. So in this case, I would say that the limit does not exist because there is no clear intended height. Now, on the other hand, if I asked what is x of 3, what is the function value at 3, the McDonald's doesn't exist here, it exists here. So the function value at x equals 3 is 1 and only 1. But the limit is not about where is the function, the limit is about where is the function intending to be. The fact that I'm going to one location from one side and a different location from the other side means that there is no intent. The function exists, but the limit does not. Now, the fact that I'm going to two different locations from two different sides allows us to extend the way we ask limit questions. Instead of just asking what's the limit as x approaches 3, I could break this into the two sides separately. In this case, 3 with the little plus sign in the upper right hand corner, that means what would happen to the limit as x approaches 3 from the right, and this one would be 3 from the left. So if I look at the graph one more time, the limit as x approaches 3 from the right means as I'm approaching in this direction. So as I'm approaching in this direction, I'm approaching 1, versus 3 from the left means I'm approaching from this direction and I'm approaching 2. So in this case, we can see visually that the limit exists because there's a break in the graph and they don't go to the same location. But another way I can show that the limit doesn't exist is I can simply look at the right-hand limit goes to 1, the left-hand limit goes to 2. If these two numbers are not the same, then the limit does not exist. If these two numbers are the same, then the limit does exist and they exist at that number. So if I'm trying to calculate a limit, I can simply calculate the right hand and left hand separately. If they're the same, then the limit exists at that number. If they are not the same, then the limit does not exist. So more formally, one-sided limits, we use a slightly special notation. Limit as x approaches a with a plus sign means from the right. Limit as x approaches a with a minus sign means from the left. And we can also say that if the right-hand limit equals the left-hand limit, and they're both the same number L, then the limit, the full limit, is that number L. So if the right and left hand are equal, then that's the limit. Otherwise, the limit is D and E. So let's look at an example. Here we have the graph of a semicircle. We're going to call this function f. Let's start with the limit as x approaches 0 from the left. So I'm going to start, here's x equals 0. Here's the actual value at 0. The actual height at 0. As we approach 0 from the left, I'm heading towards that function value of 2. As I approach 0 from the right, I'm heading to that function value of 2. And since the left hand and right hand are the same, then I can say the limit is in fact 2. So this isn't evaluating the limit necessarily by direct substitution. I'm not just looking at 0 and trying to evaluate the limit. I'm looking at the left hand and the right hand. Since the left hand and the right hand agree, then I say the limit is 2. Here's a slightly different one. Why don't you take a stab at this one? Try to think how you would answer these questions. Pause here, play when you're ready. All right, so this time we're going to look at x equals 2. Here's x equals 2. Now 2 from the left, hopefully you obviously got that the intended height would be 0 because the point is right on the axis. Now 2 from the right, here's where you may or may not have gotten tripped up. If I try to approach 2 from the right, the problem is there's nothing over here to the right. There is no graph to the right. That's like if I'm driving down a road, if I'm trying to get to McDonald's from the left, here's the road to McDonald's from the left, but maybe McDonald's is at the end of the cul-de-sac and there is no alternative route. There's only one road leading into McDonald's. So to try to get to McDonald's from the right is like trying to drive through a wooded area. You can't do it. Therefore, the limit does not exist from the right. There is no graph on the right to express an intent, so the limit is D and E on the right side. Now, to get that full limit as x approaches 2, it's just a matter of looking at these two guys. Are they the same or are they not the same? In this case, they are not the same. This one says 0, that one says D and E, therefore the answer is D and E. There is a left-hand limit for this x value, but there is no full limit at this x value. Here's another one. Now notice this time I didn't break it down into the left-hand and right-hand limits. That's something I want you to do on your own in your head. In order to evaluate the limit as x approaches -2, I'm not just going to look at -2, I'm going to look to the left and right of -2. And if the left and right agree, then we have a limit. If the left and right do not agree, then we have D and E. So take a look at each of these 4. Pause here, play when you're ready. So we have limit as x approaches -2. Here's -2. I look at the graph and I see we have a break. On the left hand, I'm going to 3, but on the right hand, I'm going to 1. Therefore, the limit as x approaches -2 does not exist. The limit as x approaches 0, here's 0. From the left and right, we're going to the same destination, so the limit would be 0. At x equals 2, now notice we have a hole here. At x equals 2, the y value is +2. We have a solid dot location. That is the function value, but the limit value doesn't matter what's happening at 2. It matters what's happening as we approach 2. As we approach x equals 2 from the left, we're going to 1. As we approach x equals 2 from the right, we're going to 1. So therefore, the limit as x approaches 2 is 1, versus g of 2 is 2. Different questions have different answers. Now the limit as x approaches 3. Here we have another endpoint situation. The left hand is clearly going to 1, but there is no right hand, so we'll say D and E, since I can't discern an intent for the right side of x equals 3. Here's another one. Pause here, play when you're ready. So with these, I'm trying to make the graphs more and more complex as we go, but hopefully you've noticed that it really doesn't matter how ugly the graph is. It's an easy question every single time. So -2 is right here. We've got a hole. Holes indicate that the limit does exist, not at the dotted location, but at the hold location. And this hole exists at a height of 1, so the limit is 1. X equals 0, clear intent from both sides, so the limit is 3. X equals 1, here we have left side going to 2, right side going to -1, so limit does not exist. And the last one, limit as x approaches 2, well here's 2. Notice we have a vertical asymptote at x equals 2. The left side of the asymptote is going up versus the right side of the asymptote is going down. Well, we're not meeting up, therefore does not exist. So these one-sided limits, hopefully you're thinking, are pretty straightforward, and I agree they are fairly straightforward, but I don't want to look at just graphical examples. I want to look at some examples that are based on just straight out functions as well. So here we have the function y equals the square root of x. Now, of course, you could simply graph the function y equals square root of x. This is one of our parent functions, one that you should know off the top of your head without having to do much thought. What the shape of this graph is. So you could answer these 3 questions simply based on your knowledge of the parent function, the graph y equals square root of x. But we could just as easily do this using another method. One I would suggest if you don't know what the graph is more of a tabular or numerical method. So if I want to evaluate the limit as x approaches 0 from the right, from the left, and then the limit itself, I can just start with a table of values. Alright, so I'm approaching 0 from the right, so I would try to think of numbers that are very close to 0. Now you might say 1, 2, 3 are very close to 0, but I'm going to say those are way too far away. When I say close to 0, and on the right side of 0, I would say like 0.1, 0.01, 0.001. Each one of these is getting closer and closer, but I'm starting with numbers that are really close to begin with. Alright, and then of course I could just say 0 itself as my destination point. So then if I take those x values and plug them in, if I plug in 0.1, square root of 0.1 is 0.316. The square root of 0.01 would be exactly 0.1. Square root of 0.001 would be 0.032, and of course the square root of 0 is just 0. So now let's look at these y values. As I get closer and closer to x equals 0, the y values go 0.3, 0.1, 0.03, and then to 0. So hopefully you can see that they just keep getting smaller and smaller and smaller until eventually we approach 0. So I'd be willing to say that the limit as x approaches 0 is truly 0. The intended height is just going to 0. Now from the left side, I'm not going to use these numbers, but I can make them negative. So left side of 0 would be negative 0.1, negative 0.01, and so on and so forth. But here we have the issue with square roots. If I take any of these and put these into a square root, I'm just going to get imaginary numbers. We've already established that if I am trying to evaluate a limit, limits need to be real numbers. If they're not real, then they don't exist. But of course, at 0, it's still 0. So here's a situation where at 0, it's 0, but as we approach 0, it's d and e. Therefore, the limit is not about what this guy is, it's about what these guys are, so d and e. And then to evaluate the limit, are these the same or are these not the same? Therefore, the answer would be d and e. Alright, using that same technique, here's something where you probably have no idea what the graph looks like. Give it a try, play when you're ready. Alright, so we'll set up a table of values just like we did before. My destination value is 1. From the right, I'll start with 1.1, 1.01, and so on, just like I did before. Plugging in those numbers, 1.1 minus 1 would be 0.1 over 0.1. 0.1 over 0.1 is 1. Doing the same thing, 1.01 minus 1 would be 0.01. Over 0.01 is still 1. Hopefully you realize that no matter what x value I plug in, if I'm plugging in a positive x value, I'm always going to get the same answer top and bottom, therefore the ratio is always going to be 1, except when I get to 1, I plug it in and I get 0 over 0, which would be my indeterminate value, or my indeterminate form. But again, it doesn't matter what this says, it matters what these say. 1, 1, 1. No matter what number I'm going to pick, it's going to be 1, therefore the intended height is obviously 1. If I do it again from the left side, now left side of 1 would be like 0.9, 0.99, 0.999. If I plug these in, so 0.9 minus 1 would be negative 0.1, but the absolute value would make it positive, so I would get a positive 0.1 on the top, but a negative on the bottom, so the ratio would be negative 1. And just like before, no matter what number I plug in, I'm going to get the same magnitude of value, except the top's always going to be positive, And if I'm on the left side of 1, the bottom's always going to be negative, therefore the ratio is always going to be -1, until I get to 1 when it's indeterminate again. But again, this guy doesn't matter. These guys show me that the intended height is -1. So what we have here is right side is 1, left side is -1, therefore limit d and e. All right, here's another useful application for one-sided limits, piecewise functions, where I have a function behaving like this on the left side of 1 versus it's behaving like this on the right side of 1 or at 1. So if I asked what's the function value at 1, I would use the bottom half instead of the top half. And these are just as obvious as they look. If I want to evaluate the limit as x approaches 1 from the right, I would use the function that is defined on the right side of 1. This is less than or to the left. This is greater than or to the right. So to evaluate the limit as x approaches 1 from the right, I would use this guy, plug in 1, I get 0. Versus limit as x approaches 1 from the left, I would use this guy, plug in 1, I get 1. So then the limit comes down to, are these the same or are they not the same? They're not, therefore d and e. Now, again, function value versus limit, not always the same thing. Sometimes they are, sometimes they aren't. They are completely different questions. Part C is asking me the intended height as x approaches 1. Based on the left and right hand limits, I see that there is no intended height. Versus question D asks me, what is the height? What is f of 1? If I want to know what f is at 1, I simply look for the equal sign. So at 1, I'm going to use this function, and I get an answer of 0. So the limit does not exist, but the function value does exist, and it's 0. Here's that same style of question, just over and over and over again. Why don't you go ahead and give these a try on your own. Pause here, play when you're ready. All right, let's go through them one by one, starting with the first column. At x equals 1 from the right, so to the right of 1 would be this guy right here, so it would be 2. To the left of 1 would be this guy right here, so it would also be 2. And since the left and right side agree, I can say that the limit actually is 2. Now, what is the function value at 1? Well, that's going to be based on this guy. At x equals 1, the function value is 5. So even though the limit is clearly 2, the function value is 5. So you can visualize what's going on here like one of the graphs before, where the left and right hand meet up. There's a hole at that location, and then there's a dot at a height of 5, whereas the hole has a height of 2. If I keep going, now for x equals 3, here's the boundary value, x equals 3. The right side of 3 would be this guy, 3 plus 2 is 5. Left side would be this guy, 3 plus 1 is 4. They don't agree, so d and e would be the limit. F of 3 would be based on this guy, so we'll use 4. And the last group, x approaches 8, so 8 is not a boundary value. It's clearly within this interval right here. So there's no need to do left hand, right hand. I'm just going to plug in 8. 8 plus 2 is 10, so the answer is 10. 0 is going to be clearly within this interval. It's not a boundary value. No need to do left hand, right hand. Just plug it in, and I get 1. 2 from the right. Now I'm asking 2 from the right, but 2 is clearly within this interval. It is not a boundary value. So whether I do 2 from the right, 2 from the left, or 2, it's going to be the same answer either way. 2 plus 1 is 3. And then f of -2, not a limit question at all. -2 is in this interval. Plug it in, and I get -7.